Good morning. Here we see the case study on a modified Newton's method used to solve a steady flow problem based on the shallow water equations. Introduction. Root finding method has plays important roles in engineering sciences such as fluid dynamics. It can be used to be a part of the dam's break analytic solver. It can also be implemented in solving a steady flow problem based on the shallow water equations. A good method should produce the exact solution up to the computer machine precision to a nonlinear equation very fast, and it should need only a small size of computer memory. The bisection method is the first order accurate, that is the order of convergence is of the bisection method is 1. Then the Newton method is second order accurate, that is the order of convergence of the Newton method is 2. But it records the information on the derivative of the function under the consideration for its roots. A modification of Newton's method was proposed by McGraw-Doggle, and we use the modified Newton's method to solve a steady flow problem based on the shallow water equations. We compare the results with those of the bisection and the standard Newton's method. The number of iterations to solve the problem is taken as the parameter to access which the method performs better than the others. The rest of the paper is organized as follows. Modified Newton's method. The first step is recalling the standard Newton's method. The formula for standard Newton method is xn plus 1 equal to xn minus f of xn divided by f dash of xn, where n starts from 0 up to infinity. Then it's extended to the modified Newton's method. Then consider the differentiable function f of x, that is f is a function of x. Assume that this function has one root and we seek for the root with the initial value x naught for the root. The standard Newton's method, that is the given formula. Then modified Newton's method works as follows. The initial iteration takes two steps, that is x naught double dash equal to x naught, then x equal to x minus f of x naught divided by f dash of 1 by 2 into x naught plus x naught double dash. The next iteration for k equal to xk equal to xk minus f of xk divided by f dash of 1 by 2 xk minus 1 plus xk x double dash k plus 1. We are interested in the derivation of the standard Newton's method, can consult with some textbooks on numerical methods of numerical analysis, which usually also covers the bisection method. In this case study in shallow water flow, in this section we present a case study of a mathematical model for a steady flow problem based on the shallow water equations. Consider a one-dimensional channel. Water flows steadily from left to right. The water depth at the left end domain is equal to the depth at the right end. In addition, the water discharge at the left end is also the same as the discharge at the right end. There is a parabolic distribution as a part of its topography. The steady flow is illustrated in the given figure 1. The steady state flow can be modified using a cubic equation which comes from the shallow water equations. We derive the cubic equations as follows, that is HR equal to h of uk at k equal to 0. Here the free variable at the time t and space x, and the dependent variables are the velocity, that is v. The depth h of x comma t, that is h is the displacement and t is the time. The topography z of x is given. The constant g is the acceleration due to gravity. Another form of the shallow water equations can be found in the work of Mungassi. Then we can assume that u1 h are smooth. Then we obtain u1 of ut h plus u into ht plus u of hx plus 2 into ux into uh plus g into hx plus gh zx equal to 0. Then the solution of ht from the mass of the equation number 6 this into the equation number 8, the results are ut plus u into ut ux plus g into h plus z of x equal to 0. Here the figure it is an illustration of steady flow over a parabolic obstruction. The curve on the top is the water surface. The curve at the bottom is the topography. As the flow is steady, the water depth and the velocity are independent with respect to the time t. That is ht equal to 0 and ut equal to 0. So the shallow water equations can be rewritten as u h of x equal to 0, u into ux plus g of h of z of k equal to 0. We can, integrating the given equations 10 and 11 with respect to the variable x, we can obtain the solution u into h equal to q and 1 by 2 into u square plus g into h of h plus z equal to c for some constant q and c. Okay. Then equation 6 and 7 hold for the whole domain. Far from the obstruction, the topography, water depth and velocity. That is z of x comma 0 equal to 0 and h of x comma t equal to h naught and u of x comma t equal to u naught are the points we have uh equal to u naught h naught respectively. Therefore, the given equation will become like this. Then we can eliminating u from the equation number 5 using equation number 4. We can get the equation that is u equal to u naught h naught divided by h. Therefore, the given equation becomes like this. Then using the constant f naught that is equal to root gh. Therefore, the given equation 17 can be expressed as u naught. Then the given equation 19 is solved for its root for all the points in this space domain. In this section, we represent our numerical result for a test case for the implementation of the root finding methods to solve the steady flow problem. We assume that all quantities are in SI units. Okay, the values are given. Okay. The numerical results are summarized in the table 1. We observe that the modified Euler method requires only 4 iterations to solve the problem, which is slightly lower than the standard Newton's method that requires 6 iterations. And also the bisection method needs about 6 times of the number of iterations required by the modified Newton's method. It is clear that regarding the number of iterations, the modified Newton's method is better than the bisection method and standard Newton's methods. Note that all of these methods produce the same solution given in the table. Okay, here we conclude that the steady flow problem has been solved using modified Newton's method. We conclude that the modified Newton's method is more better than comparing other two methods.